Welcome to the kinematics of rigid body motion. Today we are going to discuss the Euler angles. The direction cosines we have studied so far are nine dependent quantities. The six orthogonality conditions given by equations 4.9 or 4.15 reduce them to three independent parameters. Apart from these constraints, the transformation describing the rotation of a rigid body must also be of determinant +1. And to see this, we can look at the following arguments. The inversion of the coordinate axis is given by the matrix S, which is simply the identity matrix multiplied by -1. And using the multiplication of matrices, we can decompose this as the product here. This matrix simply corresponds to a rotation about the z-axis by pi radians. However, the matrix here is the problematic one, as it does not correspond to a rotation. Rather, it is a reflection of the z-axis in the xy plane. So, therefore, an inversion of the coordinates axes cannot be accomplished through a rigid transformation of the axes. A physical displacement of a rigid body never corresponds to an inversion. And for every transformation matrix A having the determinant -1, there exists a matrix S such that A is the product of the matrix S multiplied with the matrix B, where B has the determinant +1. And as such, this matrix does not correspond to a rigid change in orientation. The transformation matrix being sought always has a determinant of +1. Another way to look at this is to consider the argument of continuity. As a transformation changes continuously from identity, it cannot have a discontinuous change of the determinant from +1, which is considered the proper value, to -1, which is the improper value. And you can easily see the reason for the discontinuity, because assuming that the transformation were continuous, at one point the determinant would have to be 0, which corresponds to a singular non-invertible matrix. So, in order to study the Lagrangian mechanics of rigid bodies, we require three independent coordinates that specify their orientation. These coordinates must be chosen in such a manner that the corresponding orthogonal transformation matrix has the determinant +1. For these coordinates, we can then write down a Lagrangian and derive equations of motion. The most important choice of such coordinates is known as the set of Euler angles. We can go from one set of Cartesian coordinate axes to another, assuming that they both have a common origin, by means of three successive rotations in a given sequence. The Euler angles are precisely the three successive angles of rotation. The choice of angles is somewhat arbitrary, and the convention used here is the one relevant for classical mechanics. Namely, it goes as follows. Starting from the original XYZ system, first we rotate counterclockwise by an angle phi about z to obtain the new coordinate system xi, eta, and zeta, which we then rotate again counterclockwise through an angle theta around xi, and we reach the primed version of the system. And finally, we rotate counterclockwise by an angle psi about zeta prime in order to obtain the final system, which is the primed version of xyz. And the coordinate axis xi prime is known as the line of nodes. Now, the transformation presented here is equivalent to the matrix product of the three separate rotations. And the matrices are given as follows. This is the matrix D, corresponding to the rotation by an angle phi counterclockwise about the original z-axis. Then the matrix C is the rotation in a counterclockwise sense by an angle theta about the intermediate psi axis. And finally, the matrix B is the rotation in counterclockwise sense by angle psi about the intermediate zeta prime axis. The complete transformation is represented by the matrix A, which is given by the product of the three matrices, and it is straightforward to calculate that it has the structure here, which, if you recall, is exactly what we obtained back when we studied a set of three particular rotations parametrized in terms of the director cosines. Now, in order for things to follow logically, you can, for example, calculate the transpose of A to obtain the matrix here, and then it is straightforward to check that A multiplying with its transpose is equal with the identity matrix. So the transpose is equal with the inverse of the transformation. And furthermore, it's also very straightforward to show that the determinant of the matrix A is equal with 1. The choice of the first rotation axis is arbitrary, and no two subsequent rotations can be made about the same axis. So these are essentially the rules by which we can establish a given set of Euler angles. And this leads to a total of 12 possible conventions in a right-handed system. For classical mechanics, we adopt the so-called X convention, which is presented here. In quantum mechanics, the Y convention is preferred, particularly for nuclear and particle physics. So the Y convention simply amounts to rotating about the intermediate Y-axis instead of choosing the X-axis. And in summary, we have established that the rotation of a rigid body is described by a proper orthogonal transformation. We have parameterized the transformation matrix in terms of the Euler angles in the X convention, and in the following we will discuss the Cayley-Klein parameters. So, with that being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.